Welcome back. The objective of this video is to represent complex numbers in polar form. Recall when we first studied complex numbers were split into two parts, their real part and their imaginary part. So we have the format a plus bi, where our real part was the a, was always on the left-hand side, and then the bi was the imaginary part. And I asked you to write it in that order at that time because I knew we were coming back to this. So we've got our two components of complex numbers, our real part and our imaginary part. And remember that an imaginary number would be like the square root of -1 or some negative square root. Well, we're going to plot points or complex numbers on the complex plane, and we'll use two axes similar to what we did for our Cartesian plane. Our real axis will be the a value, or the leading number in the a plus bi, and the imaginary axis will be our former y-axis. Okay, and that'll be the bi part. So we've got a real axis, which is the old x-axis, and the imaginary axis, which is the old y-axis. So, and we can plot ordered pairs A, B on this particular plane. So we're going to plot these points here in example 8 on the complex plane. So A, capital A here, is 3 plus 4i. So our A value is 3 and our B is 4i. So we'll go 3 out on the A axis, or our former x axis, and we'll go up 4 on our former y-axis, and there is point A at 3 on the A and 4 on the imaginary. Point B is 0 and 2i, 0 and 2i, that's just going to be right there, B. C is at -2 on the A and 3i. Well, it's going to be right there at C in the second quadrant. D is at -4, 0i, so our quadrantal here, point D. And -1, -2i, so -1 on our x-axis, -2, that's in the fourth quadrant. There's point F. And G is at 3 on the x and -I, so there would be point G. Now we'll study absolute value of complex numbers, so we'll find like the magnitude or the length of them. We're essentially finding the radius. So they say here OP has magnitude, length, and direction. So you guys that have studied vectors know that vectors both have magnitude and direction. And it says OP, my guess is this O is the origin and this is point P here. Has both magnitude and direction. So the modulus, or absolute value, of the complex number z equals a plus bi is the absolute value of z, or of the square root of a squared plus b squared. So if that looks like our distance formula, and if it looks like we're doing the Pythagorean theorem, you've got it. This is kind of like x squared plus y squared, isn't it? Equals r squared. So tangent of theta is b over a, or if you will, y over x, its slope. And the arctan of b over a, if a is equal to 0, will give us our theta is equal to the arctangent of b over a. So really, note, if a is less than 0, then theta of, or our arctan, will have to move quadrants. So we're saying if x is negative, or if a value is negative, we'll have to move our value to quadrant 1 or quadrant 4, because we can only evaluate the tangent, or we're going to evaluate the tangent in those two quadrants, right? So we evaluate tangent between -pi/2 from -pi/2 to pi/2 radians. And this diagram here, what we're saying that this is our magnitude, our z value, or our hypotenuse, and we've got our b value and our a value, or our y and our x, what they used to be, and this is our angle theta. So that's what's going on there. We can tie all that in to that diagram. So find the magnitude of z and find theta, then graph z equals -5 plus 12i. I would probably graph -5 plus 12i first. So I'll go -5 on the real axis, and I'll go 12 on the imaginary axis, and I'll plot that particular point. And we have a triangle like that, so there's our theta. So you might know that this is a 5, 12, 13 right triangle. So we can say that the magnitude of z is equal to 13, or we could do the square root of a squared plus b squared equals the magnitude of z, which is the square root of 25 plus 144, or the square root of 169, and sure enough, we know that that is equal to 13. Our theta, we'll need our calculator for that, to put that in radian mode. So we need a calc, but we're going to do the arctan of y, or b over a, or 12 over -5. So we're going to put that in our calculator, and our calculator for radian mode is going to spit out -1.176 radians for theta, or it might spit out or give us a value of -67.38 degrees for theta. But those angles, those that are in the fourth quadrant, they're down here in 4, and you can clearly see we're working up here in quadrant 2. So we're going to have to add pi to our -1.176 radians, and we're going to have to add 180 to our -67.38 degrees. So we get theta is 1.966 radians, or theta is equal to 112.62 degrees. Now that theta, of course, is from our positive x-axis. That is going to be this angle right here is the theta that's giving us. Example 11 is a little bit more manageable. Find the magnitude of z and find theta. Then graph z equals -7i. I would plot -7i first. So -7i is going to be plotted somewhere right there. Okay, well, that shouldn't be too tough to find. The length from our origin to that point, how far is that? Well, we don't even need to do x squared plus y squared equals r squared. We should know that magnitude of z is equal to 7 units. That's 7 units long. And our theta, we can eyeball that as well. That theta is going to be -pi/2. You might also see that as 3pi/2, depending on the range that we're asked to find. But this theta is in our range for tangent. And that wraps up our first video on the introduction to polar or trigonometric form of complex numbers, finding the magnitude of that radius, finding the theta, and we'll get some more practice with this when I see you in class.